Hello, everyone, and welcome back to your YouTube channel. And welcome to this very interesting, informative, but very short video today. We are working with power electronic converters. Power electronic converters are installed in many devices inside the electrical power system. But power electronic converters are enabled the low carbon technologies to grow in a very fast way. And the performance of these power electronic converters has strong influence on the power system operation and control. For that reason, today we are presenting a very short video related what we call the power chart of power electronic converters. Power chart is one of the many names that you can find in many books about this representation. What we are talking about today is the representation of the performance of power converters in terms of the active power and reactive power. For that reason, what I call here power chart can be found in many other books with the name PQ curve. Okay? P for active power, Q for reactive power, PQ chart, PQ curve, PQ plot. There are many names for this. But the job today is to discuss a bit about the use of this PQ curve, the most important equations that define the performance of these power electronic converters. But before we start, let me clarify again that those videos are for just very basic introduction about this topic. And all the opinions and all the concepts expressed in those videos belong to me. For that reason, I would like to be very careful and I would like to say be careful with the interpretation of the concept that we are presenting here because the author is not responsible for any error, confusion, or malinterpretation coming from the use of those videos. But after the disclaimer, what I want to invite you is that you joined into the ResearchGate. ResearchGate is a social media for academics that allow us interchange or give for free or most important product, research products like scientific papers, slides, technical reports, and so on. I highly suggest if you are an academic or if you are a power engineer in our industry and you want to keep up with the science, please join to ResearchGate. On the other hand, many of my classes and tutorials, there are so many codes and there are so many examples, practical examples, numerical examples, and I put all of them inside my GitHub repository. For that reason, I highly suggest that you go to the GitHub and have a look if you can find something that could be useful for you. Here, as you are watching this video, I believe that you are inside my YouTube channel. And there are many other videos for you at the YouTube channel. But if you like this video and you would like to subscribe to the channel, I highly appreciate that you do so. Finally, but not least, I highly suggest that you join into the social media, and if you want to keep up with the information of the most recent developments of the science and engineering, well, please follow me on my different social media environments like Twitter or LinkedIn. And if you would like to go straight for one question, I just include here at the very bottom my email address. Well, it's time to go for business. And power electronic converters, they arrived in electrical power system many decades ago. But just in recent time, the economy and the technology have evolved so much that they are more and more attractive for many applications. As I said before, power electronics has been around for many decades, especially for the transmission systems. There is something called the HVDC transmission system that has been for many decades, and it's probably one of the most developed areas for power electronic converters. However, in recent times, the pressure for the environmentally friendly sources has pushed a lot to the use of more environmentally friendly generation coming from the solar or coming from the wind power. From that reason, today is very, very typical found PV power panels everywhere, and inside them there is power converters to connect and to deliver the electricity to the classical AC system. Also here we have the representation of wind turbine type 4 with the full rate converters, or also we have here the type 3, that is the double fed induction generator connected with a full AC, DC, AC chain, okay? But most recently, power electronics at the demand side has evolved. The most used application for power electronic was inside the industry with those electronic drives that they can control the rotational speed of the single cage induction machines. But with the reduction on cost and the improve of technology, many new low carbon technologies like electric vehicle, battery energy storage, and so on, they appear and they are going very fast inside the market. The conclusion here is that we have power electronic converters everywhere, from the power generation point of view, from the transmission point of view, to the distribution point of view, and finally to the houses. But in this video today, we are concerned of the most important part of this power converter change. Low carbon technologies, they can use a change of power converters, several converters connected in cascade to do different jobs. But the most important one for the discussion today is the last one, that is the interface with the grid. We call this converter the grid-connected power converter. It's basically the power electronic converter that is taking the energy from the wind turbine, from the PV, from the battery energy storage, and delivering into the classical AC power source. And all the converters in general sense, you can imagine here like the schematic diagram of a generic energy conversion system, where we have here the most important part, the power part, and this is the power converter. Here is where we produce the magic of converting one input power into output power. Of course, but the power converter is nothing without the controllers. And believe me, there are many, many control loops in a power electronic converters. Some some control loops are related with the input, some others related with the output with many references. Just for a very, very short introduction here, you can see this is a type 4 wind turbine generation system. As you must remember, the Type 4 wind turbine generation is a full rate converter. For that reason, here we have a rectifier going from AC to DC. Here we have a DC to AC converter or inverter. And finally, we are going into the grid. Of course, there is a DC link capacitor over here, and there are some filters from the AC side. But what is very relevant for you to understand is that there are possibility of many type of controllers when we are working with low carbon technology. They are basic functions and they are very advanced functions. Depending of the low carbon technology that you are using, some features can be available and some features no. For instance, here on the basic functionalities, of course, you can identify that we have here the MPPT, or the maximum power point tracking. That is a classical functionality that you will find in any modern variable speed wind turbine. But also you have the current control, the grid synchronization, the grid code compliance. But the modern wind turbines, they have more and more features. More features like power quality, virtual inertia, power oscillation damping, and black start. What I am trying to tell you is that this power converter change is able to deliver many functionalities, and those controllers and monitoring functionalities, they play the key role of delivering those services. Here, there is something similar for the solar PV system. The solar PV system, as you can see over here, we are still using the MPPT, the current control, but also we can have some other functionalities like the grid support. Modern electric vehicle charging stations, they have the possibility of working in a bi-directional way, and that allow us to offer services from those electric vehicles. And many of those services can be vehicle to grid or smart grid or demand side management and so on. And they represent very advanced functionalities of control and monitoring. My favorite one, the battery energy storage. The battery energy storage is a very key role for, let's say, to increasing or to maximizing the integration of the low carbon technologies because allow to store energy and be used when it's needed. From the basic functionality, we can identify several of them, like the balancing mechanism and the battery management system, but also we can have advanced EMS, hybrid power plants, fast frequency support, and so on. In general conclusion, what I want to tell you is independently of the low carbon technology that you are using, a voltage source converter will be the interface to the grid. And this DC AC converter is basically with the filter together, the main component delivering the active and reactive power to the grid. And all the previous discussion was to tell you that the power electronic converter has many, many functionalities. One way to represent the performance of the power electronic converter is that what we call the power chart. The power chart or PQ curve or PQ chart is basically a graphical representation of the active and reactive power operating points, possible operating points of the power converters. It's defining what is possible to deliver in terms of active and reactive power from the converter. And of course, it's related with many of the possible operating limits of the power converter. To start the discussion of the PQ chart, let's consider the most general device and probably the best device to explain everything here. Sorry, and that is the battery energy storage. The battery energy storage usually use what we call the battery pack. The battery pack is the connection of many, many batteries using series and parallel connection that we can deliver high voltage and high currents. And from there, we can use that DC supply to deliver active and reactive power to the power grid. Of course, the voltage source converter have an internal voltage, and there is a series reactor that is typically a filter, and then we have the point of common connection. That is where the power electronic converter is typically delivering the service. But in this case today, we are including an external grid, and that external grid is very simple, is an equivalent reactance connected to an ideal voltage source. And the idea is that you understand that the connection of the inverter or the power electronic converter to the AC grid is related with the grid characteristic. Well, if we are working in a steady state, if we are considering only the fundamental frequency, the performance capability of the voltage source converter can be represented in a single plot, and that plot is the power chart that you can represent the active and reactive power operation. Basically, this power chart represents the limits of active and reactive power or the capacity of this converter to deliver those powers. Those limits, performance limits, are based in several indicators. In a very general way, you must understand that the maximum voltage that the voltage source converter is able to produce depends on the topology of the switching devices and also the modulation technique. For the case of two-level and three-level topologies, this voltage is directly related to the DC voltage. For that reason, it's not only the power converter topology, it's also the primary voltage, direct voltage that we use to supply the converter. And there is a relationship between the DC and AC voltage that can be provided, and also is depending on the DC voltage that we supply to the converter. And very important limit is the maximum converter rating. The current that this device can deliver to the grid. And that current is very important because the power electronics is very sensible to overheating and also to be destroyed because of currents. For that reason, the maximum converter current is related with the maximum current available or possible by the switching devices. Well, here, let me go to the next slide. We have a very, 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 very simplified, you can see that I say very several times, because this is a very, very, very simplified circuit model for representing the situation, the original situation. On the left-hand side, we have in this circuit the voltage source converter, the internal voltage of the voltage source converter. We have here the voltage drop across the equivalent reactance. In this case, we are combining the filter reactance plus the external grid. And finally, we have here the ideal voltage source, VAC, that is the voltage of the external grid. What I am telling you is that this is a very simplified, lossless representation, and you can apply here the classical Kirchhoff voltage law, and you can get that the voltage, internal voltage of the converter is the sum of the voltage drop across the reactant plus the voltage of the external grid. On the right-hand side, you can see a very interesting phasor diagram. We can assume that the reference is the voltage of the external grid. This is the internal voltage of the voltage source converter. And here you have the voltage drop across the reactance, the external equivalent reactance. Of course, this voltage is 90-degree angle compared with the current, but there are two very interesting limits that we can show here. One of them is the maximum voltage that the converter can synthesize or can produce, and also the maximum current that can be delivered by the power converter. From that phasor diagram, it's very simple to create two important relationships. The first relationship is to define the active power that is produced by this very simplified circuit representing the voltage source converter. As you can see here, the active power is the product between the magnitude of the AC voltage, the internal voltage of the power converter, divided by the equivalent reactance, and what is extremely important is the sign of the angle delta. Delta is basically the angle between the AC voltage and the voltage of the voltage source converter. That means this small angle here between those phasors over there. Of course, that equation is very simple because there are no losses in this equivalent circuit. But on the other hand, we have the equation for the reactive power. The reactive power that is delivered to the AC voltage source has this very important expression that you can see depend of the AC voltage and depend of the voltage source converter voltage. And in this case, the equation is a bit more complicated because we have here some reactive power losses through all the series components, like the reactance of the converter plus the reactance of the external grid. But this representation, this phasor diagram, is basically a voltage and current phasor diagram. We can convert the voltage and current source phasor diagram into a mm, into a power representation. What we need to do is basically create a constant factor, and that constant factor is K, that in this case represent the voltage of the external grid, and divide by the equivalent reactance. If we do so, we can represent now what we know as the reactive power, the active power, and the apparent power for the operation of the power converter. And what is very important from this representation is that now we have a representation that is a circle, and that circle is defined by the maximum current of the converter. But on the other hand, we have this other circle that is defined by the maximum voltage that can be produced by the power converter. But moving forward, the classical representation or the typical representation of the PQ curve or the PQ chart for a power converter has a strong relationship, as we said before, with the voltage at the external operating point. Because in this case, if the voltage is equal to one, well, if the operating voltage is one, we will see that the circumference or the circle is totally inside of this rectangle defined for the points 1 and -1 for active and reactive power. But if the voltage is above 1 or below 1, of course, the semicircle will be outside or inner the rectangle that we have over here, the square that we have here. What is very interesting is that usual specification of voltage source converter is defined by this rectangle, because in theory we want the voltage source converter providing as maximum active power we can get, and maximizing the delivery of the active power is reducing the capacity to deliver the reactive power. However, some most recent application of the voltage source converter are changing the paradigm. And for most recent applications, we can maximize the reactive power production, but you must recognize that maximizing the reactive power production, you are reducing the capacity of delivering active power. Which one of them is the best? Well, everything depends on the application and your interest of using the power electronic converter to delivering either active power, or more reactive power. Finally, to conclude this very interesting video over here, what I want to show you is in a single PQ curve, the representation or power chart of several technologies. As you can see, the most complete of them is the battery energy storage, because the battery energy storage is basically a circle that they can deliver active or reactive power in both directions, because the battery can be charged and discharged, and also they can deliver reactive or inductive reactive or capacitive reactive power. The solar PV system is a bit restricted. As you can see, they belong just a semicircle to the right-hand side. And the reason is because the PV system is only able to deliver active power in a range that could be from the maximum and minimum reactive power. There is no possibility of the PV system consuming active power. That is the reason that the PQ curve for this very specific device, the PV inverter, is just located on the right-hand side. But the StatCom and the synchronous condenser, they are almost a straight line that is able to deliver maximum, minimum reactive power in both directions, capacitive mode or inductive mode, because those devices are strategically designed only for this purpose. They cannot typically deliver active power. And finally, the most beautiful but the most complex PQ representation is our glamorous and very lovely synchronous generator. The synchronous generator, always there is a minimum limit of the active power production that is related with the prime mover. There is a maximum active power production that also is related with the prime mover limit. But inside, we have here the underexcitation limit, the wind and region heating limits, the armature heating constraint, and the field current limits. As you can see, depending of the technology used, you will have a different PV curve. Now, the question is, which one of these is better? Well, this is not a one-to-one comparison because the PQ performance is only one of the many, many possible elements to consider when we are selecting the performance or defining the performance of one low carbon technology. For that reason, I just want to present here one of them, and that is the power chart. Well, it's almost time to close this very important video. And today what I have done is basically I present to you different concepts related with power electronic converter. Today the power electronic converter is located everywhere from the generation point of view, transmission until the demand side. The demand side has been very fast growing. The integration of low carbon technology basically thanks to the characteristic and the flexibility provided by the power electronic converters. When we talk about the low carbon technologies, well, we must understand that those power electronic converters, they have several control loops that they can do many functionalities. They are basic functionalities that they are typically the inner control loops, and they are also more advanced monitoring and control functionalities that they can be included, like black star, like damping power oscillations, and so on. But in this video, I focus on one of the, let's say, one of the way to represent the performance, the steady state performance of the power electronic converter. And in this case, I was talking about the PT curve, the active and reactive curve that allow you to see the performance, how in a steady state the converter can deliver active and reactive power. And this curve is also including the limits. And the limits of active and reactive power production in converters is related with some elements that they are internal from the power converter, like the current limits related to the switching devices, the voltage limit that is related to the synthesizing and the topology of the power converter, but also related with the primary energy source because we require a minimum DC voltage in order that the converter can deliver the functionalities. Well, I presented also a comparison between the different type of low carbon technologies, including the synchronous generator, the STATCOM, the PV inverter, the battery energy storage inverter, and a type 3 wind turbine double fed induction generator. And well, this is all for this video. I hope you enjoyed the video. If you do so, please subscribe to the YouTube channel and keep in touch. Thank you so much for watching this video. I will see you at the next one. Bye now.